Ladies and gentlemen, thank you for joining and welcome to my presentation on hot filament CVD diamond coatings for hard-to-machine materials. My name is Woda and I'm working at CemeCon in Würselen, Germany. In the next approximately 50 minutes, I want to discuss the following topics with you. We will start with an introduction on the basic principles of diamond coating technology. I will highlight the special role of the substrate we want to coat when we are coating cutting tools. We will look how we are doing multi-layer diamond coatings by morphology and engineering, and we will apply these coating onto cutting tools and will study various case studies. These case studies include CFRP machining in the lightweight market, graphite machining in the 3C industry, as well as milling of zirconium oxide materials in the dental industry. And last but not least, we are looking at one of the most challenging tasks in cutting tool operation, which is the milling of sintered carbide. Let us start with our coating material. We are here interested in pure diamond. On the left-hand side, we see the composition triangle of carbon-based systems, including sp2, sp3 content and hydrogen. Diamond contains 100% sp3 bonds and is located at the very top of this composition triangle. DLC, which stands for diamond-like carbon, is something completely different to pure diamond. On the right-hand side, I've listed some of diamond's extraordinary properties. Apparently, diamond is the hardest known material with a 10,000 Vickers hardness. It shows a very high thermal conductivity, which is able to compete with metals, although it is an electrical insulator with a large optical band gap. However, it is also possible to produce conductive diamond coatings when the application demands this. Diamond is chemically inert. Diamond is biocompatible due to its carbonic nature, and diamond has a very high electrochemical window in aqueous environment, which allows water purification processes, just to give you an example for an application apart from the cutting tool business. We might ask now how our diamond coatings are produced. In this schematic view graph, we can see the two major coating techniques for diamond. On the left-hand side, we've got hot filament CVD, and on the right-hand side, we've got microwave CVD. Both techniques have the same basic setup. We introduce a hydrogen-methane gas precursor mix into a vacuum chamber and have a source for the activation of energy to allow the chemical reactions. In the case of hot filaments, we've got the filaments providing thermal energy to the reactor. In the case of microwave, we've got a microwave generator which ignites a plasma in order to transfer the energy to the process. Both techniques have their benefits. For the use on cutting tools with complex geometries, hot filament is the method of choice. On this slide, we pay attention to the basic principle of hot filament CVD diamond coating. We've got three regimes. On the left, we've got the filaments. In the middle, we've got the chemical reaction and transport. On the right, we've got our substrate. Let us start with the left-hand side. The filaments are metallic wires which are heated up by electrical current to degrees of about 2000 degrees Celsius. This is enough thermal energy to allow dissociation of the molecular hydrogen into atomic hydrogen. This atomic hydrogen can reduce the introduced CH4 methane to a CH3 methyl radical. Further on, another contribution of the hydrogen can generate free surface places on top of the substrate via etching. The dangling bond of the CH3 methyl radical can attach to another free carbon bond on top of the surface. This can either be a diamond seed in the starting phase of the process or the growing sp3 network later on. The substrate, which is our cutting tool on the right-hand side, deserves some extra attention I want to address on the next slide. Cutting tool industry uses cemented carbide. Typically, tungsten carbide with a cobalt binder is used here. As cobalt in the presence of diamond coating leads to graphitic formation, we have to avoid this process. Thus, we have to apply pre-treatment processes in order to remove the cobalt in the near surface region, or we can apply diffusion barriers. In detail, these processes can be very complex and complicated, especially when we consider that we want to coat more than 200 different carbides on a production level. However, it is possible to fulfill this task by applying careful acceptance procedures as well as doing careful quality control in a continuous manner. So we are able to coat cobalt-containing carbides with a range of 3 to 12% of cobalt content. We can now wonder what type of thin films we want to coat and what we are able to coat. By tuning the process parameters like gas, composition, temperature, or pressure, it is possible to tailor the morphology of the thin films systematically. An example of such a coating morphology series is shown here. Commonly, diamond is classified into 3 different groups. With grain sizes of about a micron or more, we've got microcrystalline diamond. We can reduce the grain sizes to some tens or hundreds of nanometers, ending up with the so-called nanocrystalline diamond, or we can reduce the grain size to sizes below 10 nanometers, where we have the so-called ultra-nanocrystalline diamond. Being able to do this process and to control it is only one step further to allow a very well-known and established concept in coating technology. This is coating of multilayer coatings. We are able to coat diamond multilayer coatings which show very high adhesive strength. We are able to coat very smooth top surfaces, and we have got a built-in crack resistance mechanism at the same time. We now apply these diamond coatings onto cutting tools and validate their cutting performance. We start with a case example in the modern aerospace industry, where we are interested in drilling carbon fiber reinforced plastic materials. Here in this plot we can see the results of such an experiment. We have shown the axial load which is measured on the tool versus the cutting path. We know that the onset of the increasing behavior is directly correlated to the tool life of the cutting tool. Here we can unravel the clear benefit of the multilayer diamond coatings, as we have an increase of about a factor of 8 when we compare the uncoated reference to the diamond coated cutting tool. Taking aerospace industry and CFRP as one of the leading edges in lightweight market, we can now wonder what are the open market potential in this sector. Here we see a market forecast for the near future of lightweight materials. We see that about an increase of about 500% is possible and predicted within about the next 10 years. Graphite milling has always been an important topic for diamond-coated cutting tools. In the upper right picture, we see a typical example of a mold used for modern mobile phones. In a comparative case study, here we examine the machining of graphite milling with diamond-coated cutting tools. Again, we start with an uncoated reference and detect a value of 20 meters cutting path. In contrast, we have 400 meters boost in tool life when we use the diamond-coated tools. This factor of 20 is a typical number when applying diamond coatings onto tools and machining graphite. Next, after lightweight materials and graphite, we are here looking at an example in the medical sector. Nowadays, tabletop and on-site milling devices have become very popular at dentists to produce dental implants on a very short time scale. Here we are seeing a comparative study on milling translucent zirconium oxide material. Whereas the uncoated reference only has a tool life of 4 pieces per tool. The diamond coating reference shows an impressive 30 pieces per tool. As the last of the 4 case studies on different workpiece materials, I want to now present an application on milling cemented carbide. First of all, let's look at the motivation to approach this challenging task. We are here seeing a comparison of the process flow in order to produce a mold made out of sintered carbide. In the upper conventional process path, we have 3 process steps which include green machining and the very resource-intense production of an electrode and its corresponding electrical discharge machining process. We now are able to directly mill the mold. It is possible to save up all these 3 process steps. The significant improvement on process time and cost becomes obvious in this case. In addition, it is also possible to improve the workpiece quality in terms of the stress of the mold. In this slide, some recent results of a coating called carbide speed are shown. We are here milling a 20% cobalt carbide with a ball nose end mill at the listed cutting parameters. So we are using very high spindle speeds here, and we are able to remove almost 500 cubic millimeters of sintered carbide material with the help of the diamond coating. Whereas the uncoated or PVD coating is not able to perform this task at all. So finally, the mold maker has the opportunity to gain an improvement of about 500% on productivity in terms of saved up process time. With this, I would like to summarize and conclude my talk. I've introduced to you the basic principles of hot filament diamond coating. We've looked at the special role of the cemented carbide as a substrate on cutting tools. We saw that by morphology engineering, we are able to enable multilayer CVD diamond coatings, and these coatings can be used in various application cases where we are dealing with very hard to machine materials. These include machining of CFRP material in the lightweight industry, graphite, zirconium oxide based ceramics, and last but not least, the machining of sintered carbide. I hope you have found some interest in my presentation, and you are very welcome to contact us if you've got any questions. Thank you for your attention.